Hopefully it doesn't affect all the slides. Just kidding. So my name is James McNellis. I'm a developer on the Visual C++ libraries team, where I maintain our C standard library. And this talk is nothing about that at all. I'm not a Unicode expert by any means, but Scott had sent out a list of possible interesting topics for the tutorial track at this conference. And he had listed Unicode and C++ on the list. And I said, well, that actually sounds like an interesting topic and a good opportunity to dig in and learn a lot about it. So if I say anything that's wrong, and you know it's wrong, please feel free to correct me. But hopefully there shouldn't be too much there. So this is not going to be an exhaustive coverage of Unicode. You could probably give a whole week-long, seminar on, all of the details. So we'll stay fairly high level. We're going to start looking at a bit of history, looking at text encoding in general. We'll look at the history of Unicode and kind of how we ended up where we are now, and because it kind of helps to explain why a lot of software systems are the way they are. We'll look at the amazing support, or lack thereof, in the C++ standard library for Unicode string processing. And then we'll look at a couple of libraries that can help with that. So before there was Unicode, since Unicode has only been a standard for about 20-something years, obviously we were processing text in computers. So how did we do that? And we can start by looking at single byte encodings. If we only have a small number of characters, then we can store one character per byte. So for example, in English, the predominant encoding now is ASCII. And it has 32 control characters, and then it has 95 printable characters, which are these here, plus the space, which can't be seen. So this is really great if you have English text, because that's all the letters you really need to represent most English, but it's not so great for most other languages. But the way that ASCII works is, you have a string with, a sequence of characters, and these are abstract things. It's the letter H and the letter E. So we're not talking specifically about any font issues or, how it's displayed on the screen. And we map these characters to what we'll call code points. And these code points are just numbers. In most cases in the slides, I'll use hexadecimal values, and I won't have the 0x prefix just because it would get very messy very fast. So one advantage of ASCII and other single byte character sets is that there's a one-to-one mapping between code points and characters. So there weren't 256 characters on that screen that we looked at a minute ago. ASCII is actually only a 7-bit character encoding, so it only requires 7 bits to encode each character. We don't need to this was used in the past, for example, where you might need a parity bit, or if you had a system with, for example, a 36-bit word, you could fit 5 characters into a register. But nowadays, generally, we just store them as 1 character per byte. So given that we've got a whole another 127 values that we can store in that byte, we can store, or 128 values, we can use those to represent other characters. And so what ended up happening is different groups started extending ASCII. So for example, IBM had code pages for their various systems. Mac OS had an 8-byte or an 8-bit extended ASCII encoding. DEC had one. ISO standardized a number of them. We'll look at one of them. But there's a ton of these. So for example, if you had an IBM PC, the default code page was this code page 437, which had all of those ASCII characters that we looked at before, and also all of these other characters. And these are useful, for example, if you have a limited amount of text in other European languages, you can use the characters with diacritic marks to represent that. They had these nice box lines for just drawing different shapes on the screen, and then some various mathematical symbols for if you had a spreadsheet software or software that did math kind of things. So this is just one example, though. Like we saw on that slide, there were a whole bunch more. Mac OS Roman, for example, instead of having this set, had, for example, the typographically correct punctuation marks, that sort of slant to the right and left, so you can represent text very nicely. So ISO standardized a number of extended ASCII character sets in this standard 8859. They based these basically on sets of characters that were common on typewriter keyboards at the time, or computer keyboards. So this standard is, there's no further work going into this because of Unicode. They've disbanded the working group. But so, for example, one of the encodings is Latin 1, which lets you encode, again, all of the ASCII characters, plus a bunch of characters, and this is sufficient to represent 29 European languages completely. So, this is widely used in Western Europe, for example. There's a couple of characters, extra characters that are required for example, French, and some of that was fixed in a revision of this, the Latin 9 encoding. But if you're in an Eastern European country, like if you're in Russia and you want to write text, then you might use the Latin Cyrillic encoding, which has the Cyrillic letters. So if we take a look, this works basically the same way. I believe this says hello in Russian. If it doesn't, then blame Google Translate. So if we have this string and we want to encode it in the 8859-5 encoding, we'll just take each character and map it to its matching code point using the table. And decoding text works the same way. If you have this sequence of characters, then you can decode it by mapping back to the character to get your string back. But you have to be careful, because you have to make sure that when you're encoding and decoding, you're using the same character set. So if you encode, for example, this Russian string using the Latin Cyrillic encoding, and then you try and decode it using the Latin Greek encoding, you'll get gibberish. It doesn't mean anything. So single byte encodings, there's a lot of nice features. Each character is the same size. For languages that have only a small number of characters, the text is very compact. String operations are generally very straightforward. Since you have a small number of characters and they're really well defined, functions like toUpper or is digit are really simple to implement, and they're really simple to understand. But there's not enough code points to represent all of the characters. Not only are there not enough code points to represent all of the characters in all of the European languages, but there's some languages that there's more than 256 characters, period. So it makes text interchange difficult because you end up with different encodings, and we need another solution anyway for languages with more characters than we can represent. So one solution to this are variable length encodings. These are also sometimes called multi-byte encodings, and when we use that, we don't mean, for example, an int may be 4 bytes. So you could say that's a multi-byte object. But when we say multi-byte character set in this context, we mean that we may have some code points that are represented with multiple characters. So an example of this is the Shift-JIS encoding. And in this encoding, some characters are representable using a single byte. So it's based largely on ASCII. So if you have an ASCII string, it's represented using the same representation in this encoding. But it also has 2-byte characters consisting of a lead byte and a trail byte. And the lead byte will always have the high bit set, and it's actually a subset of those, as we'll see in a moment. And the trail byte may have any value in this case. So this allows you to represent a ton of characters. So here's kind of a mapping of how the character space works. If you're parsing along and you come across a character and it has one of these yellow code points, then you map it to the ASCII value, or there's 2 here that are slightly different. If it's one of these sort of bluish color boxes, then you map it to that character. And if it's one of the red boxes, it means that it's a lead character. So it's the first character of a 2-byte it's the first code unit of a 2-byte character. So in that case, you map them, you read the second byte, and you combine the two to compute the code point to find out what the character is. So there's one problem with this, or one big problem with this, and that is that there's overlap. So for example, here are the encodings for 3 letters. It includes both Latin and Cyrillic letters. So the letter D, of course, is encoded as the hexadecimal value 44, which is the same as ASCII. To represent this Cyrillic letter, it starts with an 84 byte, and then the next byte will be a 44. And then to represent this other Cyrillic letter, it'll start with an 84, and then the next byte will also be an 84. So when you're decoding a sequence, we come across a 44 and we map it to D, and then we come across another 44 and we map it to D. We come across an 84, we know that that's a lead byte, so we combine it with the next character to form the next code point. But there's a problem with this, and it's a problem with overlap. So if you have a pointer into a sequence and it's just pointing at some character and you want to know, is this the beginning of a character or what's the previous character before this, you have to actually walk all the way back until you can find a synchronization point. You have to find, you have to go backtrack to figure out whether this is a lead byte or a trail byte. So this sort of encoding it lacks the property called self-synchronization, where basically when you're in the string somewhere, you want to be able to tell, where does the next character begin, where does the previous character begin. So you need to maintain complex state to keep track of where you are. So this is just one technique. There's another technique, for example, ISO IEC 2022, which is a sort of a general standard for different encodings. It uses escape sequences, so like you'll see an escape character, and then from that point forward, you'll be using a different character set, and then it uses another escape character to switch back. So these are even more complex because not only do you have to walk back to find the synchronization point for the previous character, but you have no idea what character encoding you're using without going all the way back to the beginning of the string and walking forward to find out what encoding you're supposed to be using. So on the bright side, there's a substantially expanded code space. You can represent up to a few over 32,000 characters, though generally, like in the Shift.js encoding, it was fewer because of the way the encoding was designed. Some byte-oriented string operations, so strcpy will still work to copy a full string if you need, or operations that do something similar. But there's a bunch of disadvantages. It's complex to parse. Some common operations, like we saw, require a linear scan over the string. Many string operations become difficult, so this does not map well to many of the existing C APIs that we have. So for example, if you want to know if a character is an alphabetic character, you can't call isAlpha because the type that it takes is a single char. And we still have the problem that there's many different encoding standards. So there's, we have the interchange problem. You have to know what the encoding of the text is when you go and read it into your process. So let's take a look at what was done in Unicode 1 to try and solve this. So 256 characters aren't enough, and multi-byte encodings are kind of a pain to work with. So how about we use 16 bits per character? So the Unicode started off with 3 design goals. It's designed to be universal, so they want to be able to represent all characters that are likely to be used in text interchange. They want to be efficient, so it should be easy to parse plain text. So we don't want any of those escape sequence type encodings or multi-byte encodings that require you to backtrack to figure out what the character is that you're looking at. And they want it to be unambiguous. So once a code point is assigned to a character, once they say this number represents this character, that won't change, and it always means exactly that. Finally, it's important to note that Unicode is just a set of characters. They're abstract characters, so they're not glyphs. So for example, there's many different fonts, and different fonts have different representations of characters, and that's totally fine. Unicode is not concerned with the visual representation. So in Unicode 1.0, there's a 16-bit code point. Each character is mapped to a 16-bit code point. So in theory, you can represent up to 65,536 characters. All of the characters in the Latin 1 code set that we saw before map to the same code point. So this is useful for interchange with ASCII data, since ASCII is a predominant character encoding, because you can just take, for example, the code point 44 and just expand it to 16 bits, and you still have the capital letter D. And this encoding that came with Unicode 1.0 is called UCS2. And so each code point is mapped to a single 16-bit code unit. The 2 is because it's 2 bytes. So we can see here, if we have that same string hello again, we map it to code points representing each letter. For Unicode, the U+ just means this is the code point with this value. And you'll note that for this particular string, the actual values of those code points are the same as in ASCII and in Latin 1. But again, the advantage of Unicode 1.0 is that you can represent characters from all sorts of different language or different scripts, and even scripts that aren't really scripts. So here we have a Latin character, a Greek character, a Cyrillic character, Japanese, Mongolian, I guess Snow people, and Arabic. So UCS2 decoding basically works the same as it did in with the single byte character sets. You take, we're reading along, we take the next 2 bytes, we say, it's a 48, and we map it to H, and so on and so forth through the string. Does anybody see a problem with this? Yes. So this here, we've assumed that the data is in a big endian format. And if in fact it was stored in a little endian format, or if, rather, if we read it in a little endian format, if we're on a little endian architecture that we're reading this in on, we'll get gibberish, again, translating the text out. So the solution to this was to add what's called a byte order mark. And the byte order mark gets written at the beginning of text, and they use this special character, FEFF. It's just a code point like any other, but it allows you to detect whether the data is in little endian or big endian ordering. So in this case, it tells us that we're in big endian ordering, and then if we switch it and we switch all the bytes to little endian, then it's easy to see that change in the byte ordering mark. So UCS2 has a number of advantages. There's a huge number of characters that are representable. I mean, 65,000 characters has got to be enough, right? Characters from different scripts are easily combinable into a single string. And each code point is representable using a single code unit, so we don't have any of those multi-byte encoding problems. It's much easier to work with the text. But there's some substantial disadvantages. There's multiple possible byte orderings. Every character requires 2 bytes. So for example, if you're moving from one of the ISO encodings that we looked at before to this, your text is going to be twice as large. And finally, none of the byte-oriented string functions work with UCS2 strings. So you can't use strcpy to copy one of these because, as we saw, the terminator for the string is 2 bytes long. It's 20 bytes.
James?
Yeah.
Question: this FE, whatever, FFE, FE, was it supposed to go at the beginning of each stream, or is it like only for file encoding of the?
So usually it goes into the file or whatever is being used for interchange with other systems. Once you have the string in your software, it's kind of assumed that you're using a consistent character encoding or you're keeping track of it otherwise. But for example, when you're writing a file, you want to make sure that you write the byte order mark. Oh, I'm sorry. The question was whether the byte order mark goes at the beginning of every string or just at the beginning of every file. It goes at the beginning of the file, or whatever unit you're using for transferring data. So if you're sending data across a socket, you'd send it before you send any Unicode text. The Unicode specification says that if there's no byte order mark, you should assume that it's big endian. Though on some systems that may not make sense. So for example, Windows uses little endian by default. So in Unicode 1, this was the usage of the code space. So you can kind of see this is a representation of the 65,000 some odd values. That at the beginning we have the general scripts, which are most of the characters needed for European language scripts. We have some symbols. There's a huge block for the Chinese, Japanese, and Korean ideographs. But then there's this big block of unused characters, so this should be plenty of room. And in fact, from the Unicode specification, 1.0 specification, it says, with over 30,000 unallocated character positions, the Unicode character encoding provides sufficient space for the foreseeable future expansion. So this is a graph, and the blue line is the growth of the number of characters in Unicode in each of the versions of the Unicode standard, and the red line is shows the growth of the number of distinct values we can represent using a 16-bit integer, and you'll see that the 16-bit integers are not keeping up. So clearly, that 16-bit encoding, that nice happy land where every character was representable using a single code point, isn't going to work. So everything changed in Unicode 2.0, and it's changed gradually over time to address various issues in encodings. But we'll kind of skip over some of the details of history, and now we'll just look at where we're at today. What do the Unicode encodings look like today? So turns out we needed to be able to encode more than 65,000 characters. If I recall correctly, there's 70-something thousand ideographs in the current Unicode standard today, so just for those, we need more than 65,000 characters. So in Unicode 2.0, the code space was expanded to about 1.1 million characters, and there's a reason for that number that we'll see in a little bit. But since the 16-bit is not enough to represent a full code unit. How about the next logical number, 32 bits? So UTF-32 works just like UTF-16 did, in that there's, except that we now have 32 bits per code unit to represent each of the characters. I've had to shorten my string from hello to hi because otherwise, I'd run out of memory on the slide. And so obviously, this encoding also has, the same problem as before, that you need a byte order mark. Yes.
You're gonna jump from UCS to UTF. Can you explain the difference between the two?
Yeah, so the question was, what's the difference between the UCS and UTF? So UCS stands for Universal Character Set, and it comes from an ISO standard that's closely related to Unicode. And so the UCS2 just means it was a 2-byte encoding. For UTF, it's the Unicode transformation format, and it's just another acronym. And with UTF, the number is the number of bits, not the number of bytes. So again, it requires a byte order mark. So here we have the big endian string, and we can also represent little endian strings. So most importantly, though, we can encode encode characters that are larger than 0xFFFF. So here we have a little rabbit with a floppy ear or something. And so when the code space was expanded, basically all of the characters that were already, or that code space that was part of Unicode already, the first 65,000 some odd characters, is what's called the basic multilingual plane. And the idea is that all of the commonly used characters are there, and we'll see why in a moment. And then there were 17 other planes, 16 or 17 other planes beyond that that store supplementary characters. Most of those are not used today yet, but they're available for future expansion of the character set. So there's a number of advantages to UTF-32. Again, now we can represent an even huger number of characters. Every code point is still representable using a single code unit, and we'll see the distinction between those in a moment. Though this isn't all that useful in most practical string usage, and we'll see why much later in this talk. But there's a bunch of disadvantages here. You still have two possible byte orderings. You need the byte order mark. Every character requires 4 bytes, and as we saw, we've only expanded the code space to support about 1.1 million characters, which means that we're wasting at least 11 bits out of every one of those 32-bit units. So it's it's by no definition dense. It wastes a lot of space. None of the byte-oriented string functions work, just like with UCS2, and most importantly, nothing that was written to use the UCS2 encoding works with UTF-32 because the code units are of a different size. So because we don't want to waste all this space, we don't want to be sending all of these extra bits when we don't need them. A second character encoding called UTF-8 was created. So the 8 here means that each code unit is 1 byte. Because we sometimes need multiple code units to represent a code point, this is a variable width encoding. And so the way it works is that if you've got a character, between 0 and 7f, we'll just encode it in a single byte, and the high order bit will be 0. One nice feature about this is that this means that every ASCII string, because Unicode started, all of the ASCII characters have the same code point value in Unicode as they did in ASCII. Any ASCII string is also a UTF-8 string. So if we have more characters than that, though, we encode it using special bit patterns. So if the high order bit is set, we know that, okay, this is part of a multi-character or a multi-code unit character. And the number of bits that are set tell us how many additional code units we have to look at. So you can see here, there's 1 here, and so we know that there's 1 additional element. There's 2 here, there's 3 here, and so we know that there's how many elements are. So again, there's the nice thing that converting from ASCII, we simply expand to the Unicode code unit, and they have the same representation. Yes.
Could you go back one
yes.
slide? So I think I didn't catch on to what you were saying.
We'll take I have another slide, and I've highlighted pieces of it. Yes. But of course, again, just like with UCS2, we can represent other scripts, and we can represent characters that were not representable using UCS2, like, again, the rabbit. So if we look at that table again, it's this first bit sequence here that tells you how many characters are in, or how many, sorry, the bit sequence, or the high order bits of the lead character tells you how many trail characters there are to read. Does that make sense? So a nice feature of this that we didn't see with the other, with the previous variable width encodings we looked at, is that if you're pointing at a character, you know whether you're looking at a trail byte or a lead byte, because all of the trail bytes start with 1, 0, and there are no lead bytes that start with the 1, 0 bit pattern. Secondly, if you're pointing at one trail byte, you only have to walk back until you find a lead byte, and okay, this is the beginning of the character, and this is how many characters I need to skip to the next one. So walking both forwards and backwards in the string is relatively efficient, as long as you're going one character at a time. So there's a number of advantages with UTF-8. ASCII text has the same representation in UTF-8. There's no byte order mark because, again, the code unit is a single byte, so there's one canonical ordering of text units. Yes, Sean?
I just wanted to put one more advantage there, which is that UTF-8, because of the way the encoding is designed, if you sort UTF-8 strings lexicographically, it sorts the same way as UTF-32.
Yes. So Sean's point was that given the encoding, it turns out that if you sort these bytes lexicographically, so if you sort them, is this byte greater than this byte, and then move on to the next one, and so on, the ordering you get is the same ordering that you would get in UTF-32, and it's the code point ordering. So you get your characters or your strings out in order based on code point. So you don't need a byte order mark. However, it is permitted to put one in. Specifically, this is used in order to identify UTF-8 text in places where it might be ambiguous with other character encodings. And so its byte order mark is the sequence of bytes EF, BB, BF. And it turns out that sequence of bytes is actually, if you take the byte order code point, FFEF, and encode it using the Unicode, the UTF-8 rules that we just looked at, then that's the byte sequence you would get. So many byte-oriented string functions still work with this. So strcpy, strcat, strlen, these kinds of things still work with these strings because, again, their code unit is a single byte. Disadvantages, though, it's a variable width encoding, so if you want to know how many characters are in the string, you need to actually walk linearly from the beginning to the end to count them. And there's text for a few languages that requires more storage than in a 16-bit encoding, and I have a list of those. Yeah?
You mentioned that the byte-oriented string functions still work because they were single byte code units, but really it's because there's no embedded 0 code units. It causes them to still work.
Sure. So the point was that the byte-oriented string functions, like strcpy, for example, works not only because there's because we have a basic code unit of char of type of a single byte, but it also works because there's no embedded nulls. So that's true, but so even in UTF-16 or in UTF-32, for example, the code unit is 4 bytes. So if you ever come across a 4-byte code unit that is all zeros, then that's your null terminator. So it's yes, it's just another feature of the encoding, I suppose. Yes.
So this last disadvantage that you list here, do you mean to say that UTF-8 can't encode all of UTF-32?
No, what I mean is that text for a few languages requires more storage. I'm sorry, so the question was, does this mean that UTF-8 cannot encode all of UTF-32? No, so all 3 of the encodings that we're going to look at, UTF-32, UTF-8, and then UTF-16 in a moment, can encode the entire code space of 1.1 million characters.
It's just the opposite of the last advantage. In the first case, you're saying
yes, right.
Usually,
yes.
but one of the disadvantages, sometimes it's not.
Right. So usually the 8-bit encoding requires less storage, but there are a handful of languages where a 16-bit encoding would be more efficient. So, yes.
I'd like to characterize UTF-8 as a brilliant brilliant piece.
Yes.
If you don't,
So for people who don't know, it was done by Ken Thompson.
well, but
I did not
he
know that.
was building on previous encodings that had many of those features. I mean, it wasn't a single person, really.
Yes. So the point was, Beeman pointed out that yes, this is a brilliant encoding. Sean pointed out that Ken Thompson developed it. I did not know that. That's an interesting fact. Yes.
I want to point out, I don't think so.
Okay.
First, it requires more storage for Chinese.
Yep. So we're actually going to take a look at that. I've got a couple examples.
Another thing is it works with usual single byte based string algorithms, but it has a significant disadvantage on backward compatibility because most of the legacy multi-byte encodings works on 2 bytes, and UTF-8 usually gives 3 bytes on those languages. And
Right.
the difference between 2 and 3 is a lot different between 2 and 4.
Right. So the point that was just made is that there are some languages, specifically a number of Asian languages, and I have a list, where you can use a 16-bit encoding like the one we'll look at in a moment, and generally each character only requires 2 bytes, 16 bits. But then with UTF-8, those same characters require 3 bytes to represent due to the encoding scheme. I actually think that this is not particularly an issue, and I'll explain why in a couple slides. So we have this problem, though, that, so UCS2 is obsolete. It can't encode all the code points. Nobody should ever do anything with UCS2 ever again. But there's a lot of large systems and libraries that were built using the 16-bit UCS2 encoding because, at the time, especially in the early 90s, that was Unicode. That was good enough. As we saw, everybody, the Unicode standard even said this is plenty of code points to represent everything. So a number of big examples that people here are probably likely to run into. Qt, development of Qt started in 1992. Windows NT development started in the late 80s, but the first release came out in 1993, and so it uses a 16-bit code unit, and then Java, which came out in 1995. So because of these and a large number of other libraries and systems, the 16-bit encodings have sort of propagated to other places. So many C++ Unicode libraries use a 16-bit code unit. The .NET framework uses a 16-bit code unit for interop with Windows largely. So we need something in modern Unicode that allows us to work with a 16-bit code unit and that is largely backwards compatible with UCS2. And so the solution for that is UTF-16. And there's a couple things about this. So for code points between 0 and the maximum value representable by 2 bytes, UTF-16 is equivalent to UCS2. So if you take UCS2 text and you try and interpret it as UTF-16, that'll work fine. Also important is that these are the most commonly used code points. So most of the code points used in European languages, almost all of the code points used in Asian languages are in this first chunk, and so it's called the basic multilingual plane. So as we saw in the chart showing the code point usage in UCS2, there was a whole block toward the end that was not assigned yet. And so in order to encode characters outside of this 0 to 65,000 and some odd range, 2,048 code points between D800 and DFFF are reserved specifically for use in encoding UTF-16. So this is 11 bits of space, and so that is enough, as we'll see in a moment, to represent all 1 million values. And we'll do that using what are called surrogate pairs. So how do we do this encoding? So if we have a code point and it's between these 2 values, first we subtract the 10000 from it to give us a 20-bit number between 0 and the maximum value represented by 20 bits. We split this in half with the upper 10 bits and the lower 10 bits. And then we'll add the upper 10 bits to 0xD800 and we'll form what's called the lead surrogate. And then we'll take the lower 10 bits and we'll add them to this other number, DC00, and we'll form the tail surrogate. So I have an example of this. There's a symbol, the cocktail glass. that is not representable using only 16 bits. So I'll call this a surrogatini, since we're going to use surrogate pairs. So what we do is we subtract from it to get a value that's representable by 20 bits. And then we'll take that, I've converted it to binary because it's easier to see. We'll take the bottom 10 bits and the top 10 bits. And the top 10 bits we will encode into the lead surrogate. And the bottom 10 bits we will encode into the trail surrogate. And so those are formed just using the same steps that we had before. So there's a couple of advantages to UTF-16. The most notable one is that we get some level of compatibility with UCS2, which is important for a lot of systems. There are a few languages, and again I have the list in a moment, where text is smaller in UTF-16 than in UTF-8 in terms of the number of bytes required to represent it. But there's a lot of disadvantages here. There's multiple possible byte orderings, so you still need the byte order mark just like in UCS2. Every character requires at least 2 bytes. None of the byte-oriented string functions like strcpy again work with UTF-16 strings, just like they didn't with UCS2. It's a variable width encoding, so we have most of the disadvantages of UTF-8. And because it's larger than, since the code unit is larger than UTF-8, we have practically none of the benefits. And the last point is the point that Sean made a moment ago, is that binary string comparison. So if you do a lexicographic string comparison of UTF-16 strings, it produces a different ordering than for UTF-8 and UTF-32. So, yep.
If you go back 3 slides.
Yep.
3 slides.
3 slides. One more?
Yeah.
This one.
Oh, no, sorry.
Ah.
One more.
Oh, other direction? Okay.
Yes. So you claim that for code points between 0000 up to FFFF, UTF-16 is equivalent to UCS2. But how could that be the case if we reserve 2,000 code points out of those?
Yep. So there are no characters assigned to these code points. So the idea is that these code points will never be used in text interchange ever. Like they're reserved absolutely for use solely in composing surrogate pairs. So if you're decoding UTF-8, you should never ever come across these. If you're decoding UTF-32, again, you should never come across these. The question was, how is this second statement here true that for code points between 0000 and FFFF representable using a single code unit when we reserve code points? So.
But does that mean that in UCS2 you don't use those?
Yes. So they were unassigned in UCS2. They've never been used for an actual character. All right. So UTF-16 again has a lot of the disadvantages. So UTF-8, it's more compact than UTF-32 in all possible cases. It's a variable width encoding, so it's more complex, but it's by far the most commonly used for storage and data transmission, and it's the dominant character encoding on the internet. So I found a study online that found that out of the top 10,000 websites, 78% of them used UTF-8, and it was 65% out of the top million websites. And many of the others were using either specific encodings for different regions or other things like that. UTF-32 has the benefits that it's simple, so it's a fixed width encoding, but it has a lot of wasted space because of the large 32-bit code units. I would contend that if Unicode 1.0 had not introduced UCS2, then UTF-16 probably would not exist at all, and that its primary purpose is to support interop or that the primary purpose of UTF-16 is support interop with UCS2 old code. So as I mentioned, there are a number of languages where it takes, where if you encode a string using UTF-8, it takes more space than using UTF-16. And this is an analysis that a colleague at Microsoft did. They found there's a corpus online, and there's a link in the slide notes if you're interested, that has 160-something megabytes of text in a whole bunch of different languages. And he encoded it using the 2 different encodings to see, which languages, what the space usage is for different languages. And so you can see that at the high end, Japanese text, on average, may require 150%, of the space when encoded in UTF-8 compared to UTF-16. So these are the only languages where it's where UTF-8 may be less compact. There's about 100 and something other languages that are all more compact in UTF-8. Now, granted, some of these languages, like Chinese and Japanese, are used by an awful lot of people. But an important thing to note is that this is very dense text, right? So this is just plain text for these languages, and that's often not how text appears. Usually, for example, if you download a web page, an awful lot of the characters in that are going to be angle brackets and ASCII characters for encoding HTML tags and things like that. And so in practice, it turns out that the overhead is generally much less than 50% overhead. Yeah.
So you were saying, maybe I didn't understand your point, that UTF-16 is just a holdover because of UCS2.
Yes.
But there's this distinct advantage with.
Sort of. So yes. So if you are, if you have a large body of Japanese text and you want to store that. So the question was, there are distinct advantages in some languages for UTF-16. So there's a couple points. So first off, I think that the issue is generally not this severe because again, usually you'll have other data mixed in that's not in that language. The second case is oftentimes if you are concerned about space, like storage space on disk or transmission space across the network, you'll use some kind of compression for that. And generally, both the UTF-8 string and the UTF-16 string will compress roughly the same. There may be a few percentage difference, but it's not substantial. So yes, I would argue that given the complexity of the UTF-16 encoding, and given that UTF-32 can be used when you need a one-to-one mapping between character code points and code units, and UTF-8 can be used for practically everything else, that the UTF-16 is largely for interop, I would say. So we'll look at one more feature of Unicode before we start digging into C++, and that's dynamic composition. So here we have the letter A, which is very simple. I think we're all familiar with it. But oftentimes, it's not just the letter A. It may have various diacritic marks. And Unicode basically handles this by having, basically you have the set of what are called base characters. So the letter A is a base character, and all the other letters and other characters that can appear on their own are base characters. And then each of the diacritic marks is what's called a combining character. So for example, to represent that, we would represent it using two Unicode characters. 41 for A and then 308 for the diaresis, to combine together to form this single text element of the A with diaresis. So in general, when you're processing text, you cannot assume, even if you have UTF-32, as you're reading across the text, you can't assume, okay, I've read 32 bits, that's my next character, I can just display that on its own. There may be combining characters after it. This is an example, with that is common in many European languages. This technique is also used, for example, in Hangul symbols in the Korean language to compose syllables into words. So you can combine lots of things. You're not limited to one combining character. So for example, here we have the letter E, and we've combined it with a combining bridge below, a combining tilde, and a combining X above. The order of these of the combining marks sometimes matter. So for example, here, you can see that the combining character for the tilde comes before the X, and so the tilde is grouped closer to the E. Whereas in this case, where we've swapped the order, the X appears closer to the E, and the tilde appears above it because of the order of those. However, in all of these, the combining bridge below, the last one in both of these examples, you can put that anywhere because it applies to a different location on the character. So there's a number of problems that this causes. So not only can you not just parse text one code point at a time, but also if you want to compare strings for equality, like as we'll see in a little bit, it becomes difficult because these two, not these two strings, but if we move the combining bridge forward, then that should compare equal to the string with the combining bridge that's later. So that's enough about Unicode in theory. Let's look at the amazing Unicode support in C++. So C++ 11 adds a number of Unicode code unit types. Char, of course, has always existed, and it can be used to represent a UTF-8 code unit. UTF-16 can be represented, code units can be represented using a char 16T, and UTF-32 with a char 32T. The use of, yes?
Something that has annoyed me since C++11 came out is that UTF-8 is char.
Yes.
Instead of unsigned char, because we need all 8 bits and we do mostly do bit manipulation.
Char may be unsigned, or it may not be.
It may,
yes.
may not be. Like, that's not what we...
Yes, so the reason for that, and we'll look at that, is largely for interop with std string. Yeah?
I asked the call people for this question, and they say, if the char cannot represent all 256 possibilities, then this implementation is not UTF-8 friendly. So...
I think that, so I know that I don't actually.
It requires that.
Yeah, I know that at least POSIX requires at least an 8-bit char. I don't remember if POSIX requires an exactly 8-bit char, or if it just or if C++ requires at least, and then POSIX requires exactly. So in practice, anything that I'm talking about here, when I say byte, I mean octet. I mean 8 bits. Yes, there are embedded systems and other things that have other widths of bytes. But in practice, when we're doing lots of text processing, I think that we're generally working on systems that have an 8-bit byte. So in addition to having these code unit types, we also have, you can have Unicode string literals. So these have new prefixes. It used to be that you could have a no prefix or an L prefix for wchar-t. So now there is a U8 prefix, which means this is a Unicode, a UTF-8 Unicode string literal. There's a lowercase u, which means that it's a 16-bit UTF-16 string literal. And then there's a capital U, which means it's a 32-bit UTF-32 string literal. And you can represent Unicode characters that are outside of the normal set of English characters, either using universal character names with the \u and then the code point number, or using, if your compiler supports it, you can actually just put the characters into your text. So there's also, we can also use these as character literals, sort of. Because remember that some characters are not represented using a single code unit in each of these encodings. So for example, with the narrow literals for UTF-8, there's no extra prefix because all of the things that you can represent using a single char are what you can represent in a single code unit. So for example, if we try to represent the snowman using a UTF-8 char literal, that's not going to work because it's not going to fit. Similarly for our cocktail glass, which requires 32 bits. The same is true for char 16T. If you want to represent something that's not representable by 16 bits, that won't work. So it's only char 32T that can represent any full character. Specifically here for char 16T, I say it's wrong. I actually believe that it's ill-formed from reading the standard, but G++ was happy to compile it as is, so I'm not entirely sure. Visual C++ does not yet support the Unicode character literals. So C++ has this amazing Unicode string type. I'm just kidding, it does not. So what you can do, though, is you can use std basic string, and you can specialize it with string, U16 string and U32 string for each of these code unit types. And we can initialize them from the various Unicode character literals. But when we look at this, we have to be careful because std string just stores it's just a dumb sequence of code units. It does not store code points, it does not store characters, text elements, graphene clusters, any of these higher level things. So, if you have iterators, if you iterate from begin to end, then you're going to be iterating over code units. So you can't say, okay, this is, a character, this is another character, this is another character. Size does not return the number of code points, it returns the number of code units. Functions like front, back, operator, the subscript operator, and other things, they operate on code units as well, which makes, for example, if you have UTF-8 text in a std string, it makes it rather inconvenient. If you want to as I have an example here, if you want to push back a snowman and say hello to it, you can't just call pushback. You actually have to have the snowman in a UTF-8 string and then copy all the elements into the back. We also could have constructed a std string and used plus equal or done any number of other ways to do that. But the key here is that it's difficult to work with text, in terms of characters. And so if you take nothing away from this talk, then note that, if you're working with Unicode strings, stop thinking about characters and think about, substrings and longer sequences of text than just characters. So we have the same problem with the U16 string, and it's only with the U32 string that you can actually push back any character because each character is representable using a single code unit. So we can look at a property of Unicode strings. We can look at length, and what do we mean by string length? So if we have a simple ASCII string, the string length is actually straightforward. You just start from the beginning, and it's 1, 2, 3, 4, 5. Okay, it's 5 characters. But it's not quite so simple in Unicode. So I have here this string, and here is its Unicode representation. So it's the digit 1, the letter A, the diareses, and then the cocktail glass. And here's how it's represented in the 3 Unicode encodings. So first we can think of a string as being, okay, it's just how many bytes are in it. In that case, here I've just used alternating colors to show it's 1, 2, 3. So in that case we can just count the number of bytes. That's fairly straightforward. Secondly, we can think about it as the number of code units. And if you call .size on a std basic string, this is what you're going to get. You're going to get the number of elements that it takes to store this. We can think of it as the number of code points, right? So for example, for the cocktail glass, it may have taken 4 bytes and it took 2 code units, but it's still just 1 code point because it's a single character. Yes?
I believe that the A with 2 dots is also a single code point as well.
Yes, and we're going to take a look at that in a moment. So there is another representation, and that's going to cause us even more trouble. And finally, we can look at this as the number of text elements, the number of things that we should consider as being one whole unit of text. And so in this case, we combine the A and the diareses together, and it's one text unit that we want to treat together. So we have these different meanings of string length, and if you're using a std string or something like that, you're going to be size is going to return to you the number of code units, not the number of characters. So string equality. So for ASCII strings, this is very straightforward to think about. If you want to know if 2 strings are equal, and you can use strcomp or other functions, or the equals on std string. You're just going to walk, and compare the representations and look at the first character and the second character and the third character, and see and stop when they're not equal. And if you have Unicode strings, it's the exact same thing. You can get a representational equality by starting from the beginning and comparing each of the code units. But in Unicode, there's multiple representations of some characters, or some things, I should say. So for example, here we have the A with diareses. There's, we saw it represented as 2 different Unicode characters. But there's also a composed form of this, which is the A with diareses. And so anytime that you see these 2 characters together in a Unicode string, they should compare equal, or they should be considered equivalent to this single Unicode character. The reason for some of these precomposed forms, like this one, like it's kind of silly, why do we have both this precomposed form and this other decomposed form, is largely for compatibility with some other with existing character encoding. So for example, the Latin 1 character encoding had a whole bunch of characters that had diacritic marks on them. And the Unicode committee wanted to make sure that you could take text encoded in pretty much any character encoding, convert it to Unicode, and then convert it back and get the same string. And so in order to do that, they need to they need to have this precomposed form. But it's not just limited to diacritic marks. So as an example, there are actually two letter A's in Unicode. There's the normal one that we get from ASCII, and then there's a full-width capital letter A that is used, that corresponds to, again, for compatibility with older character encodings. There are some Asian character encodings that have what's called a full-width Latin capital letter A, so it takes up twice the normal space in a fixed-width font, so that if you want to line it up in columns with Asian characters from Asian scripts that are very wide, you can actually do that, and things line up well. There's also ligatures. So, for example, the F and the I, it may be represented by an F followed by a letter I, or there's a Latin small ligature FI that's used in typography a lot. It may not just be two characters. The Latin there are some Roman numeral characters. And then finally, we mentioned this previously before, that if you have a character with multiple combining characters like this, as long as they don't conflict, as long as they affect different parts of the letter, you can change their order in the text sequence, and they should compare equivalent. Yes.
Previous slide.
Yeah.
Eric, I'm just curious. What's the motivation of putting that into Unicode? Was there an actual use, or is it just some random encoding already had it, and Unicode tries to be all-inclusive in that regard?
Yes, so the question was, why include a character like this at all? I actually don't know the answer to that. Yeah.
Or the martini glass.
Or, yes, well, I use those all the time.
All the Mahjong tiles and domino tiles in Unicode. Unicode has all the Mahjong tiles in it.
Ah.
And all the dominoes.
Yes.
Yeah.
Can you repeat?
So Unicode has all of them, for example, the Mahjong tiles, and I know it has all the chess symbols, so for example, for chess notations. Yeah, there's whole collections of characters, but for example, why there's a Unicode snowman, I don't, I don't see that a lot in text when I'm, reading things.
A lot of these come from, there were cell phone companies that got this standardized for their formats for text messaging. And so it's a standard until it gets to go into Unicode.
So the point that was made is that there are, for example, there were some cell phone companies that put these in, and I know that that's true for some of the emoji characters, because they now have, we have this standard set of characters, let's get it added to Unicode. It's funny that we can do that, but real languages like Klingon and Elvish don't get representations. Yes? Yeah. Yes.
It's actually, whether they are equal, it depends what, the semantics of what you're trying to do. For example, if you try to align the text, then they are not equal, but
absolutely.
The meaning of the text would be equal, right?
Yes, so the point was that, whether or not these two characters should compare equal, depends on your definition of equality. And that's true absolutely for all of these, right? So, but as a counterexample, so the example that was made is if you're trying to draw text, you actually do care about the difference between these. And that's true for a lot of these. Like the ligature FI may be rendered by your text editor differently than, the character F followed by the character I. On the other hand, for example, if you're implementing a web browser and you want to implement search for it, and you type in FI, you want it to find, instances of FI and also instances of the ligature FI. Thank you. So Unicode defines two types of equivalence, basically. And these are examples. The first one is an example of the first kind, and the second two are examples of the other kind. So the first kind are what are called canonical equivalents. So with canonical equivalents, they're strings where they should be, for the purposes of text processing, not necessarily text rendering, they should be considered completely equivalent. They're the same thing. Any place that you use one, it should mean the same thing as the other. And then it has what's called compatibility equivalents. And these are places where, for example, when you're doing searching, maybe you want to consider these equivalences, but they don't necessarily need to be considered exactly the same in all contexts. And so in order to do comparisons, Unicode has what are called normalization forms. And so there's 4 normalization forms: NFC, NFD, NFKC, and NFKD. The NF stands for normalization form. The C ones are composed forms. So basically anywhere that it finds, like for example, if it found the A followed by the combining diareses, it would combine those into the precomposed form. The decomposed normalizations, on the other hand, do the opposite. If they come across precomposed forms, they will decompose them. And then the difference between the canonical and the compatibility decomposed is that the canonical, again, are the things that these things should always compare equal. And the compatibility are largely for, okay, you're doing searching, you're doing comparisons of strings. And normalization in all of these cases includes a well-defined ordering for combining marks. So if you, for example, have a string that has combining marks in a different order, it will put them into the canonical order if there are multiple valid orderings. So let's look at how we can do normalization using the C++ standard library. You can't. So if equality is problematic, what about just sorting text? So we can take, a simple example. If we've got the string containing the Latin letter A and the string containing the Latin letter B, we can just compare them by comparing the two code units. And if we have Unicode strings, we can do the same thing. But again, this is a comparison of the representations. It's not a comparison of, are these, should this one actually, appear before another? So, as an example of this, even just with the ASCII characters, so let's say we have a vector of strings, and in it we've got the lowercase Latin letters C, B, and A, and then the uppercase Latin letters X, Y, and Z, and we call sort to alphabetize the strings, and we print them out. What gets printed?
Lowercase and uppercase.
Right. Yes. So it's not going to alphabetize them. It's actually going to print all of the uppercase letters first and then all of the lowercase letters because, again, it's comparing them by their code point value. And so all of the uppercase letters have code points that appear before the lowercase letters in ASCII. So what we actually need to do in order to get an alphabetization is we need to use some locale because alphabetization and collation is fundamentally locale sensitive. It's particular to each language. So for example, here, if we instantiate or if we create the English locale for the United States and sort these, then we'll get them in the expected alphabetical order. But the reason that these are different for different languages. So we can consider, for example, the A with diareses. In the German locale, it's considered to be just an A with an accent, so it gets sorted after the A's. But in the Swedish language, it's actually considered its own letter, and it gets sorted after the Z. So if you want to sort strings, or if you want to collate strings, you actually have to know what locale you're working in. So we can look at how we do Unicode collation using the standard library. And that's also left blank. Now, so the standard library does have the std locale objects, and you can instantiate them. But the actual locale strings, the locales supported by the environment, are entirely implementation defined. So for example, on Windows, there are no UTF-8 locale support. On Linux and other operating systems, you may be able to get a UTF-8 locale. But what it actually gives you for ordering, it may not entirely match what you're expecting. So if we look at a couple other text operations, we mentioned that some of the standard library functions just don't work well with Unicode. So as an example of this, we have this toUpper function that takes a code unit and converts it to the equivalent uppercase code unit. But this expects that there's actually an uppercase form of each of the lowercase letters. And so as a counterexample, in German, there's, I believe it's called the SZ. The sharp S, okay. The uppercase form is actually two characters. It's two uppercase letter S's. So this, this API, this toUpper that returns, a single character, it's not even reasonable. Yes?
So I've heard there's an effort to make an uppercase sharp S code point which should be rendered as a double S, but which will need to go too lower to upper and,
yep.
and reverse it.
So the point was that there has been an effort to add an uppercase sharp S code point, and that has happened. I know it's in Unicode. My understanding is that there's very few systems that use it. Now, I'll also note that there's some systems that don't, that even if you have good Unicode handling, they will not do the correct conversion for this this character. For example, on Windows, we don't do it largely because it became a concern for, even if you have a full string, it became a concern that developers are not going to expect that, oh, I'm just doing a toUpper, now my string is longer. I don't know that that's necessarily a good thing, but so even the classification functions are unusable, right? So if you want to know that something is a space and you have a code unit of a char, the only way that these will work is with char 32T. So one thing that is actually fairly easy with the C++ standard library is you can convert between different encodings. So for example, here we convert from a UTF-8 string to a UTF-32 string simply by using the W-string converter. Yeah?
I'll assert that because that works at the string level rather than iterator level, that in fact even that's pretty badly limited.
Okay, Beeman made the point that because this works at the string level and not the iterator level, it's fairly limited. Similarly, you can do something, you can actually do transformations using the I/O streams by imbuing a custom locale with a code conversion facet. So for example, this program, I write out binary data, which happens to be UTF-8 data. You'll see I include the byte order mark. This is the UTF-8 byte order mark, and then a sequence of UTF-8 data. In our code CVT facet, we tell it to consume the header, which means that it will look for a byte order mark, and it will do the right thing, based on what byte order mark is there. Now you still need to tell it what what you think the source encoding is, and then this program prints out this, the sequence of code points that it's read because we're converting to UTF-32. I actually was somewhat surprised. There are no, so there are type defs for char and wchar-t stream types, but there's none for the char-16 or char-32 types. Yes?
I also wonder how well those are supported. Well, the char and the white char types usually are pre-specialized in whatever shared object or DLL
Yep.
standard library comes in. I don't know if the char-16 and char-32 versions are.
Yes, that may be. So the point was that the char and wchar-t specializations may actually be pre-specialized and be part of your standard library implementation with custom implementations, and that these other two may not be for char-16 and char-32t. Yeah, I don't actually know what the requirements are there. I know that this worked on Visual C++, which was the only implementation I was able to try it on, as libstd C++ doesn't support the code CVT header yet. Yes?
This is because I think the original design of these things in Dinkomware is that the byte string out string is treated as external encoding. So when talking to the external, we only use byte-wise operation, because when writing to file system, we always write bytes. And the white character support is largely borrowed from C.
Right. So the point was that, in general, when you're talking with the outside world, you're going to be reading in, individual bytes. So you want byte-ordered I/O, and then so that's why there may not be these specializations. But in this case, the get function on the stream to get the next character type thing takes whatever the template parameter was, and that's the type of thing that it extracts. So the standard library doesn't have a whole lot, but there's a pair of libraries that we'll look at that actually enabled you to work with Unicode. So the first of these is International Components for Unicode, or ICU. So it's a library. It's got a huge set of features. If it doesn't have what you need, I would be surprised that I would be shocked. I was trying to just read through the documentation, and it's got all sorts of stuff. It's very widely used, so it's well tested in a lot of real-world software. It runs on lots of platforms. It has a permissive license. It's MIT licensed, I think. Unfortunately, it has its own string type, Unicode string, and it uses UTF-16. And the reason that it uses UTF-16 is that the library was originally written in Java, and then it was ported to C++. Because Java uses a 16-bit character type, they used it here as well. It doesn't work well with other string types in most contexts. Usually you actually have to convert back and forth between the string types. And the library is absolutely not modern C++ by any definition of that term. Again, largely because it was a fairly direct port from Java, so the interfaces match what is done in Java in many cases. So we'll take a look at just a few of its features that try to address some of these problems that we've looked at so far. So first, it does have a UTF-32 code unit type, and it works largely just like UChar-32t or char-32t. with the exception that because it may not be a character type, you may need to have a cast to initialize it. It also has a uchar type, which is the UTF-16 code unit, and it needs and it uses this because again the Unicode string is fundamentally a 16-bit type encoding. So the Unicode string can actually do the conversion from UTF-32 or UTF-8, as we can see down here. It can also be initialized directly from a single UTF-32 character, in which case it just becomes a string containing that one character, or from a single UTF-16 character. It has a ton of operations that actually work well with Unicode. So whereas when we saw the std string interface, like a lot of the functions, they operate on code units, so they're not very useful for actually working with Unicode text. The Unicode string functions, like they actually are designed to work with Unicode text. And one of the key things here is that anywhere that you have something that returns you a character, or for example, if you want to append a character, it doesn't take a uchar, which is a 16-bit thing. It takes a uchar 32, so you can pass the entire code point, and it does all of the conversion automatically internally. So it has support for normalization. So here's an example of, we normalize this string, which starts off as a Latin capital letter A with a combining diareses, and then we normalize it according to the composed normalization form, and that gives us back a string containing just the precomposed character, the Latin capital letter A with diareses. You can also do collation. It can create collators for each locale. It returns a pointer, so you can use unique putter to handle ownership. It also has Unicode regular expressions. So I didn't even mention the C++ standard library regular expressions, which basically, if you want to use them for Unicode, first, if you want to do anything useful, you're probably going to need to use UTF-32 strings, because it's not going to handle the UTF-8 encoding internally. Second, it doesn't actually handle, there's a whole bunch of Unicode-specific regular expression features. So for example, here we want to match any character that has the property, it's a number. And then we try to match it with this string that contains 12 and 5/8 using the Roman numeral character and the fraction 5/8. And then we'll process the matches, and this will match both of those. So these interfaces, like I said, they're not modern C++. They're kind of cumbersome to work with. They don't interop well with standard library stuff. So for most basic tasks, you don't actually need to use ICU. There's a library in Boost Locale. It was introduced in Boost 1.4.8, and it's basically a modern C++ API, and it doesn't have all of the Unicode logic inside of it. Instead, it uses another backend that provides all the Unicode functionality. So, for example, it can use ICU. You have to build it with ICU support. It can use the C++ standard library, which is limited to your platform's support for Unicode stuff. Or it can use the Windows API directly, or the POSIX APIs for working with Unicode strings. So it doesn't have support for most of ICU, but it has support for most of the commonly used features. To start off with, usually you need to create a locale. So here, for example, we create an English locale with support for UTF-8. The Boost locale generator is basically like a container that stores the locales you've created, because creating them is very expensive. So we can use this for normalization. So for example, here we have two strings. The first one is the precomposed form of the Latin letter A with diareses, and the second one is the decomposed form. And it just has a normalize function that takes the string, the locale, and then the normalization form that you want to use. And we can insert at the end that we've actually done the transformation like we'd expect. It supports collation. So it has, actually one thing I also wanted to mention on this previous slide. So this is based on std locale. So you can actually use the std locale in various places where std locale is required. And it adds support for Unicode. So for example, if you're running on Windows and you try to create a locale with enus.utf8, it's going to crash or it's going to throw an exception actually, because there is no such locale that supports the UTF-8 character set. So this handles that automatically. So we can do collation. So for example here, again we have the A and then the A with diareses, and if we do the comparison, basically we get the collator facet from the locale, and then we call compare on it. It also has a nice helper that will let you use this as, for example, the ordering, the comparer for a map. So, for example, here we construct a set with this comparer. So it'll actually handle Unicode equivalents, and it'll do the correct collation when you stick things in the set. This is most useful, for example, if you're storing words in a language that has multiple representations, and you want to make sure that you only have one copy of each word. It supports, so Unicode actually has a set of collation levels. So the first one, the primary one, is that it ignores cases and accents, and it compares base characters only. The secondary one ignores case, but it still considers accents. The tertiary one considers case and accents. You can find out more about this in the Unicode standard, which we'll talk about in a moment. So Boost Locale can do conversions, so you can convert this UTF-8 string to UTF-16 or UTF-32. You can convert the UTF-16 string to UTF-32, or you can convert back to UTF-8, which is implied by char. Yes?
Can you convert to from other code pages?
Yes. And that's actually what I've got on this next slide. So I have, thank you. So here we have the Cyrillic string that we had from before that says hello. And we're going to convert it to UTF-8 using the right ISO encoding. So it also has a whole bunch of functionality for string-based case manipulation, for example. So you can call toUpper on an entire string, which gives you the correct semantics you need, for example, to handle different numbers of characters. It has boundary analysis. So here we construct a segment iterator, and we iterate over characters. Now, I contend that this is misnamed because what this actually iterates over are text elements. So it'll find blocks of a character with all of it, a base character with all its combining characters. So this usage of the word character doesn't match the way that Unicode uses it. But basically, the idea is that we're going to iterate over text elements. So for example, here. You can see that the byte length of this string is 8 because, again, it takes 8 code units, UTF-8 code units to represent it. But if we iterate over it using this segment index iterator, we only get 3, which is the number that we would expect. 1 for the 1 for the A, and then the diareses, the two characters together, and then 1 for the cocktail glass. Yes?
When you say that the A there is, or the A with the diareses on, is actually 2 code points, doesn't that depend on how you actually save the files?
Pardon?
Doesn't that depend on the encoding of the file?
So the question was whether this is the composed or the precomposed or the decomposed form, the one that takes just 1 character or 2. Doesn't that depend on the encoding of the file? Actually, yes. And so when I did most of my testing, because Visual C++ doesn't yet support Unicode literals, I actually had to put in the Unicode using the universal character names, the /U followed by the thing. But yes, you're right. Your text editor might save it, in a different form than you typed it in. That's totally possible. So Boost regex can also sit on top of the ICU regex engine. So for example, this is an example of doing regex matching for the same thing we had with ICU. Basically, it works just like with the regex token iterator, except you can use the U32 regex token iterator instead. And then it'll iterate over the various matches. So we'll look at, there's two, I was looking for, okay, so the standard library support is fairly poor. What has been proposed for standardization? And there were 2 proposals that I found. One of them that Beeman wrote is a proposal to adapt the standard library strings to support Unicode a little better, and specifically to support different encodings. So for example, the paper proposes to add new constructors and new assignment operators to a basic string, so that you can take a basic string with a different encoding and initialize the string with it. So for example, you could have a U32 string and initialize a std string from it, and it would do the correct conversions. Plus, there were new overloads for the formatted I/O operators and new encoding conversion iterators. The second paper was also interesting. It was proposed by Mark Boyle in December, I think the paper was put out. And it proposes a new string type, because we should, of course, have a new string type. And the string type is called encoded string. It provides a slimmed-down stood string-like interface. And all of the operations are on code points, not on code units. So when you iterate over it, even if you're using UTF-8 where you may have 4 bytes, 4 code units representing a single code point, when you iterate over this string from begin to end, you'll just get the code points. This has the distinct disadvantage that iterators are bidirectional only, because you can't have random access when you don't know how large each of the elements is. So there's that. So I have a number of resources here that I recommend. The Unicode Explained book, it's an O'Reilly book. It was interesting, fairly comprehensive and thorough. The Unicode standard is surprisingly easy to read, much easier, I have to say, than the C++ standard. And it has a set of annexes and technical reports that go with it that are they're very interesting. They talk about a lot of the problems that people run into. They talk about a lot of issues. Has an enormous FAQ that even has an FAQ about the FAQ. So there's a lot of information there. You can find the Boost locale library. Boost no-wide is not a Boost library yet. I saw it's in the review queue, but there's no review manager or whatever. And what this is it's basically a library to make working with Visual C++ and Windows platforms a bit easier with, since most of Windows uses UTF-16. If you want to use UTF-8 and narrow strings in your app, it can be difficult. So for example, if you pass a narrow string to fopen and it contains UTF-8 characters, it's not going to do what you expect. You need to convert to wide characters and then use we have a wfopen function instead. So he's got a library here that re-implements some of those functions to make it a bit easier to work with. There's this website, UTF-8 Everywhere, that's sort of like a manifesto written by a handful of people about why UTF-8 should be, the encoding that is used, everywhere, with fallback to UTF-32 when you actually need the, the one-to-one mapping between code points and character and code units. And there's a nice discussion on one of the Stack Exchange sites of should UTF-16 be considered harmful. So, with all that said, are there any questions? Yeah.
Can you go back to any one of your slides that has a UTF-8 literal? There was some right towards the end there.
Yes.
Yeah. So this gentleman up here asked a question about your editor, which is very valid because you're typing in something and the same encoding process is happening when your source file gets saved and the compiler reads it in. So first of all, does this standard say anything about what the encodings of source files are?
So the question is, does the standard say anything about the encoding of source files? It mandates that there is a basic execution character set, which basically is a selection of the ASCII characters required to represent all of the C++ things. And at compile time, you have to support all of those. I don't actually think that it requires that the compiler handle Unicode text, as input. And that's why, for example, we have the universal character name literals, the \u with the text. Did you? Yeah.
I have a proposal in front of the core group that the standard continue to support source encode, any source encoding they want to, but that they always support UTF-8.
Okay. So
and because, and there are two reasons for that is why that specific thing is proposed. One is because UTF-8 is a wonderful standard to propose for that use. The other is all compilers that we could quickly get any information on already supported UTF-8. Mm-hmm. There's a little bit of an issue of with or without byte order marker, but
right.
That's something the core group could work out. And I'd like to reactivate that proposal and push that out, because right now you cannot write a C++ program and ensure that it's portable to any compiler, because the compiler may simply not read the character set that you wrote the program.
Yep. So Beeman's point was that he has a proposal before the core language group that to basically continue permitting compilers to support any character encoding that they like, but also to require that they support UTF-8, both because it's a useful encoding, but also because at least today there's basically no way to write portable C++ source code because your code is dependent on some encoding, and what your compiler supports is not standard. So, yes.
So I have a question. You mentioned like that UTF-32 is basically one-to-one code point with code units.
Yes.
And UTF-8 can be up to 4 right now, right?
Yes.
So my question is like once the Unicode raised to the point where the 32 is not enough, like how far, why should we consider char 32 as one-to-one, and how far UTF-8 can go? Like, is there still availability in the UTF-8 where we can extend it to encode more than 4?
Yeah. So the question was, what happens when basically 4 billion characters is not enough. But actually, we don't have 4 billion. We only have 1.1 million due to the UTF-16 encoding rules. So. Yes, on the one hand, like I don't want to, be like Unicode 1.0 was, where they were like, oh yeah, 65,000 ought to be enough for anybody. Right, yeah. I don't want to say that, but on the other hand, 1.1 million characters is a lot, and we're only using 10% of it about at this point in time.
Well,
now,
these people put in like rabbits there.
Yes. Yes, there. If we had a character for every animal out there, then yes, we might run out. So so when UTF-8 was originally standardized, it supported up to 6 code units. So you could actually represent much more than just the 1.1 million. They restricted it when they decided, oh, we need to support this UTF-16 thing. So let's restrict it so that you can encode the same code space in each encoding form. So from that respect, it's artificially restricted. At some point, if they decided, okay, we're throwing UTF-16 out the window, then in theory you could just expand the UTF-8 encoding to support up to 6 or more code units. I think 6 is the practical limit because the number of you have to be able to encode the number of trail bytes in your lead byte. Yes.
You could just let the encoding go into, let the lead byte introduce the next lead byte.
That yes. So there are a lot of options, but so the suggestion was, oh, you could just have the one lead byte introduce the next lead byte. That is certainly. There's certainly options. I think that any speculation here, like I don't think this is a short-term problem, or even I hope that we don't run into this problem before I retire. So we'll let our children deal with it. Yes.
I'd like to make a comment, and that is that the reason that C++ standard libraries does not have good support for Unicode is not because of a lack of interest on the committee's part or a lack of realization that it would be wonderful to have such support. It's because no one has stepped forward with viable proposals.
Yes. So Beeman has said that it's not that the standards committee is not interested in Unicode support, and I'm pretty sure that everyone on the standards committee would love to have good Unicode support, but it's that nobody has submitted viable proposals at this point. So write a paper. So yes.
How about the font sign? When you're going to represent 100,000 different characters, it's a big hassle to draw all those pictures. Is there like a default set of images that you could use as a font provider and only make the interesting characters your own style, or how does it work?
So the question is, what do we do with actually rendering all of these characters? So if there's 1.1 million possible characters, and there's only 100,000 now, but even that's a lot. If you go and create a new font, do you have to go and create glyphs for each of these? So there's two things. The Unicode standard has sort of like an example representation of each glyph. It's there for exposition only. It's not this is the only way to draw it. I know that I don't know how it works on other systems. I know that on Windows it'll use fallbacks if it can. Some software will. So for example, if you're typing in some font that doesn't support a character, it might fall back to one of the symbol fonts that's available, or one of the more complete Unicode fonts. But otherwise, you know, like maybe if you're typing along, you'll just get the box like I had in as a joke at the beginning. So, does that answer?
I'd like to interrupt you. You
Yes.
can ask more questions after.
Okay.
Before people start to leave, Patty has set out leftovers from last night. She's got some fresh vegetables and stuff, but the chicken and I think there's still some hamburger left from last night. It's down where we had the picnic last night. So if you don't want to go into town, there's not enough for everybody, but if you want to avoid the trip in town, you don't want leftovers, that's an option.
Excellent. Okay, so I've reached the end of the presentation. We've reached the null terminator. So if you have any questions, I'd be happy to talk later.